Hello everyone, this lesson is about symmetry and determining whether or not functions are even, odd, or neither. And those are very similar topics, although there is a bit of a difference between them. So there'll be a strong similarity. So it's a fairly short lesson. This one is kind of just introducing the symmetry. If you look at this graph, what you can see here is that almost like fold lines when you were younger and you may have seen or made some sort of an art project, and a dotted line would indicate maybe a fold line. If you can fold something and it ends up with one half of it exactly hitting the other half, then that is a line of symmetry wherever that is. And so you can see here on these three objects we have several lines of symmetry. Now I just have a little note at the bottom. Some figures have rotational symmetry. All of these do, in fact. And that occurs when there's a point that you can rotate the object about, and it would still look identical. And then we talk about how many degrees to rotate it. So you can see that this point of symmetry is in the center of each one of these. That's not always the case, but that is very common that's what we look at, particularly if on a graph that center point ends up being at the origin. So first of all, just what a line of symmetry is. So then, as we look at these particular things, these are math graphs. Where would we have a line of symmetry? So we could have a line of symmetry right here, where the left hits the right. Same thing here. This one's going to pick up a couple of extra ones because we have, or at least one extra one. We have one there. But also, and I can't draw this horizontal line on here, on that x-axis, if we could fold the top to the bottom, it would fit. Now, we don't want to do this diagonal one because if you look closely, this section here sticks out further than the other one, so it wouldn't actually hit if we fold it that way. But this does have two lines of symmetry. Now, if I fold this one vertically, it does not hit. And if I fold it horizontally, it does not hit. However, I'm going to put a little yellow mark there. This is not a line of symmetry, but if you visualize spinning that, kind of like a pinwheel around that point, you could get this tip to spin around to that tip. So if we spun it 180 degrees, 90, and then 180, it would end up hitting the other one. So this one actually has that point symmetry. We'll talk a little bit more about that in a bit. Now, if I did the vertical line here, that's not going to work because this arrow to the left would end up to the right. It's not going to hit itself. If I do a horizontal line here, that's also not going to work. They end up going the wrong direction. But yet this one also has point symmetry. So those do not have line symmetry, but these have point symmetry. That's not really what we're looking for right here, but it is important to something coming up, okay? And that point happens to be right there at the origin. So I'm going to say it's at 0, 0. Now, for line symmetry, what you're generally dealing with then is just trying to visualize, you know, when you have that chicken and we have stabbed it with a spit, maybe a sort of thing. I guess the rotisserie chickens at Walmart or something. The top part looks like the bottom part. Now I know realistically if we actually spin it, the back doesn't look like the front, but where that little upper wing is, it would end up where the bottom wing is. Just so you just kind of have to visualize, could you spin these graphs in the same way? Well, that line of reflection we talked about, we are particularly interested in it if it is the x-axis or the y-axis, or if it has point symmetry at the origin. See, I mentioned that. Okay, point symmetry at the origin. So which is it each one of these has? Now I drew the lines before, but this one was a vertical line and that line is the y-axis. So this one has y-axis symmetry. This one had both x-axis because I could fold it horizontally, and y-axis because I can fold it vertically. This one had the point symmetry at the origin. This one on the bottom left here, this one had y-axis symmetry. And again, this one had point symmetry at the origin. Okay, now each point of symmetry is described in a particular way. Then we're going to say it's symmetric with respect to the, and I didn't write that phrase down, but with respect to the, it's symmetric with respect to the x-axis, or it's symmetric with respect to the y-axis, or it's symmetric with respect to the origin. And that origin I know is not a line, but actually it says, let's talk about that relationship here. I want to talk about how it does relate to a fold. So on these where we had a fold, if you could fold this down and then fold it over, so it's two folds, folded over the x and then over the y, those points would hit each other. And the same thing happens here. If you folded, and this time I'll do it up just because I draw the line better. If you were to fold this one up and then fold it over the line, it hits here. So it is related to folding, but you actually have to do two folds to get that origin symmetry, okay? So sometimes you'll just be given graphs and asked to be able to inspect them visually and see if they have any particular type of symmetry. And then you can verify that it's true algebraically, and that's something they're going to tell you over and over and over. But before we get into that, then let's just go ahead and say what type of symmetry each of these has. So here the fold line would be the x-axis. So this one has x-axis symmetry. But what I'd point out then is if you look at this point and then the one that it mirrors below it. They have the same x value, but the y values are different. I know that this is 4, 2, but let's just say that this one is xy. Then this one that mirrors it underneath has the same x, but it has the opposite y. If you wanted to verify it algebraically, then what you can do is replace y with the negative of y. So if you take this y value and you replace it with the negative y, you should end up with the same x value. So look at how that applies up here. If I take this y value and I replace it with negative y, and then I simplify it, negative y squared actually is the same thing as y squared. So I replaced y with negative y, but when I simplified it, I got the exact same answer. That is how you can verify x-axis symmetry algebraically. So if it has x-axis symmetry, replace y with negative y. By contrast, this next one has y-axis symmetry. If you look at it on the graph, what we can see is that the points that mirror each other. But if we pick this point up here, that one has a positive x value and a positive y value. But the point that it mirrors has a negative x value, but the exact same positive y value. So in that case, if it's got y-axis symmetry, what we see is that you can replace x with its opposite, and you get the exact same value. So if I want to do that up here, if I replace this x with negative x, then I'll have 3 negative x squared minus 2. But when I simplify that, I get 3x squared minus 2, exactly like I had to begin with, because when you square it, that negative goes away. So when we have y-axis symmetry, you can replace x with negative x. For x-axis, we replace the y's with negative y. For y-axis, you replace the x with negative x. So what happens when we have this origin? Well, let's look at a point. This point right here, I'm making it big so it really shows up, has a positive x and a positive y. Actually, that point on this graph is the point 1, 1. But the mirror, and again, to do the y-axis, you would need to fold it twice. The first fold would bring it to here, and the second fold would bring it over to here. But because we are folding twice, what happens is that we end up with both the opposite x and the opposite y. Okay? So here we replace both the x and the y with the opposite of x and the opposite of y. And it should be equivalent. So if I take this function up here, and by the way, I didn't write that one down, but this one is origin symmetry. Negative y equals 1 over negative x. But that, look, then if I multiply both of those by a negative, I end up with what you can do to simplify it. So because I want y equals, when I multiply, divide or multiply by that negative there to get just y, it changes this one back to 1 over x. So x-axis symmetry, replace y with negative y if you need to verify it algebraically. Y-axis symmetry, we replace x with negative x to verify it algebraically. For symmetry with the origin, you can replace them both, and they should end up being exactly the same thing. Now, before I move on, because we've got the next topic coming up with the even, odd, and neither, the reality is, as you're doing your homework online, you will have questions that ask you to verify it's true algebraically, but you can probably tell by inspection or just by looking at the graph what type of symmetry it has. So don't overly stress over that material. Moving into even and odd functions. Both even and odd functions, to test for that, you don't want to replace any y's. So we're not going to, it's going to be a little bit different, but we will replace x with negative x, okay? In both cases, replace x with negative x. So I'm going to write that up here at the top. Whenever you want to test even and odd functions, always replace x with negative x. Then when you do that, you simplify it and look at the results. Notice here that this says that f of x, which means when you plug in the regular x, will equal the exact same thing you got when you plugged in the negative x. Okay? There's no difference between them. That is the definition really of the even function. If you plug in the negative x, you get the same thing you got when you plugged in the x, which is even. So I have a little note down here. This is just my note that if it's even, it's exactly the same, because that way you can focus in on those first letters to help you remember it. If you get the exact same result, it's even. By contrast, if you look at this definition of the odd function, if you plug in the negative x, you get a negative in front, which really means that's the opposite. So if you plug in a negative x, you get the opposite, okay? And that is odd. So if you look down here in my notes, just underneath that, odd functions will give you the opposite. Even functions give you the exact same result. Odd functions give you the opposite result. And it's possible that neither one is going to happen, that some of the signs change and some of them don't. But if it's not exactly the same, it's not even. If it's not exactly the opposite, it's not odd. So if neither happens, it is simply neither. So functions can be even, odd, or neither. Now, before I move to the next slide, just one other thing I would want to point out, and that is that all of this is dealing with functions. So if you have a graph that isn't a function, this does not apply, okay? And remember, a function has to pass the vertical line test, and it also has to be, for every x, there's exactly one y. So before I go to the next slide, let's just back up to an early slide here. When you look at this one, this first one is a function. Every x has one y. So is the second one. But this third one is not a function. We have an x value over here just to the right of the origin, and it has both a positive and a negative y value, not a function. This one, this bottom left one, this one is a function. But the next one over is not a function because we have two y values directly above each other. So that means it fails the vertical line test. So if we were talking about even, odd, and neither, we could not use it at all on this last one or on this third one in the top row because they are not functions. And even, odd, and neither only refers to functions. So now let's look at this then. These are some graphs we saw before, but if we only replace x with negative x, okay, and that is the only thing we're going to do, if I take f of negative x, I have 3 times negative x squared minus 2. And then I simplify that and I get 3x squared minus 2. Now compare that to the original, and what we see is that that is the exact same thing we had to start with. And if it's the exact same thing, that function is even. Now you might say to yourself, no, wait a minute, I thought that one had symmetry. Well, it does. Those are two different categories. Even functions, this is even, but that doesn't mean it didn't have the y-axis symmetry. It did have y-axis symmetry because we actually used that same test for y-axis symmetry. So if you already know something has y-axis symmetry, you can say that it's even without going through this test because that was the same process. When I was talking about how to verify algebraically, to verify the y-axis symmetry, we would replace x with negative x and see if we get the same thing. So even functions do have y-axis symmetry. Okay, now let's look at this next one then. If I replace x with negative x, I get 1 over negative x, which in its best simplified form, I could just bring that 1 to the front and say that's 1 over negative 1 over x, but that is the opposite of what we started with. Since that's the opposite of what we started with, then we ended up with odd. Okay, so that one is odd. And again, now what type of symmetry did this have? It had origin symmetry. So here's the deal. If it's got y-axis symmetry, it's even. If it's got origin symmetry, it's odd. So what's the deal with the x-axis symmetry? Well, here's a kind of a summary slide, and this is kind of a key one. You might want to take a picture or take a snapshot, screenshot of this slide. On y-axis symmetry, down here underneath this very first graph, you can replace the y with negative y and get the exact same x value. However, even, odd, and neither does not apply at all because this one is not a function. It fails the vertical line test for an x value. It has more than one y value. So we're never going to talk about even, odd, or neither with that particular case. All right. Now our other ones, if it has y-axis symmetry, you can see down here, that's the very first thing I wrote, but the last thing I wrote is even. If it has origin symmetry, last thing I wrote is it is odd. Now how can you test those? You can test those algebraically with replacement and see how they work. Let me share just before we finish up then, that's our last slide on there, but let's look at a homework problem or two and see how this is going to apply for you. So like test algebraically whether the graph is symmetric. So they didn't draw the graph on this one. On several of them, they do draw the graphs. So let me just kind of back up and let you see. Here it'll say graph the equation. On this one, you can just punch it into your calculator. It's in a y equals form if you need to, so you can figure out which one it is. And then you're going to see if it's symmetric. But on some of them, they don't have that multiple choice on there. So let's just kind of look at that. First of all, if you were going to, let me back up one. Let's use this one. If you were going to test if it's symmetric then this is where you're plugging in, if you want to test the x-axis, plug in the negative y and see if you get the exact same thing. If you want to test the y-axis origin, plug in negative x and see if you get the exact same thing. And to test the origin, you have to plug in both negative x and negative y and see if you get the same thing. Okay? So I'm gonna, I can't do those on here, but I'm just gonna kind of talk you through that because I'm on a different screen. But if I plug in negative y, let's plug in negative y first of all to test our x. If I replace this y with a negative y, when I square it, it becomes exactly the same. No other part of this function is selected. So if I test for x-axis symmetry, it does have it. If I want to test y-axis symmetry, I need to plug in negative x, but negative x squared is the exact same thing. So it also has y-axis symmetry. If I want to replace origin symmetry, I test them both. They both become the exact same thing. So this actually has symmetry with respect to the x-axis, the y-axis, and the origin. This is where that last slide is going to help you find the point that is symmetric to this point with respect to the, okay, x-axis, y-axis, and origin. But if you have a point like 7, negative 7, if you have 7, negative 7, then the other one is going to be 7, positive 7, because it just changes that y-axis. And you can see how you can use that to help you out on some of that homework. Another type of problem they have is determined visually. Is it even, odd, or neither? So they didn't give you an equation. But what I can see here is that this one has symmetry with respect to the y-axis. And so just taking that information, and let's go back over and look at the summary slide. If it has y-axis symmetry, it is even. Okay? So again, I think this slide will help you a lot. And you just get in touch with me if you have any questions along the way.